The partial adjustment model is a dynamic time series model where the dependent variable depends on an exogenous explanatory variable, but where the dependent variable takes time to adjust. So the setup for this model is as follows. We have time series data on a dependent variable y and an explanatory variable x. The idea is that yt is affected by xt, but the full effect takes time. So if there is a sudden change in xt, yt will slowly adjust to a new value. To model this behavior, we introduce a new variable called yt star. The idea behind this variable is that this is the value that yt would take if we had no inertia in the system. That is, yt star is the value that yt would take if the adjustment was instantaneous. So yt star is a theoretical variable, it's not actually observed. Here is the partial adjustment model. We assume that the latent variable yt star is determined by a linear regression model such as this one, where nut's are the error terms of this model. Yt star is not directly observed, but instead we have an adjustment process. And the adjustment process, according to this model, is as follows. There will be a change in yt. So yt minus 1 is the increase in yt from the previous period to this current period. And the assumption is that this increase, the actual increase in yt, will be a proportion of the increase that would happen if we had no inertia in the system. Remember, yt star was the value that yt would take in the absence of inertia. So yt star minus yt minus 1 is the increase in yt due to changes in xt and due to the error term that we would observe in the absence of inertia. Well, the actual increase in yt, the left hand side, is a proportion of this, and this proportion is determined by the coefficient lambda. Say for example that yt star minus yt minus 1 is 1. In an inertia-free environment, yt would increase by 1 unit. If lambda is, say, 0.4, then the increase that we would observe in yt is 0.4 and not 1. So this is the reason why it's called a partial adjustment process. We don't have a complete adjustment unless lambda is precisely equal to 1. This adjustment parameter lambda is also called a speed of adjustment. And the assumption here is that this lambda must be greater than 0, there must be at least some adjustment, and it's less than equal to 1. If it's equal to 1, then the adjustment is instantaneous. That would correspond to the case of no inertia at all in the system. The smaller the lambda, the smaller the adjustment, that is, the smaller the speed of adjustment is. So the partial adjustment model is the combination of these two equations. This is unknown, so if I plug this into the second equation, I have the change in yt is equal to the speed of adjustment multiplied by the latent variable is determined by xt and the error term, and then subtracting yt minus 1, that's the increase. Now if I expand this parenthesis and move this one to the right hand side, I have yt is equal to lambda theta 1, that's the intercept, plus lambda theta 2 xt. The terms in front of yt minus 1, there is a plus 1 from this term here, and there is a minus lambda from this term here. So plus 1 minus lambda yt minus 1, and we have the error term, lambda nu t. So let's just rename these parameters. The product of lambda and theta 1, we rename that to beta 1. We rename this to beta 2, and we rename 1 minus lambda to rho. We create a new sequence of errors called epsilon t. Each epsilon t is just lambda times nu t. Then our partial adjustment model can be written as yt is equal to beta 1 plus beta 2 xt plus rho yt minus 1 plus epsilon t. And if you look at this model, you see that this is exactly an ADL 1,0 model. So there are a couple of ways to view this. The first one is to realize that the partial adjustment model is just a special case of the ADL 1,0. Another way to view this is that a motivation for using the ADL 1,0 model is the partial adjustment process. If I specify a model as an ADL 1,0, then I can do that using the argument that I believe that there is some inertia and it takes some time for the y variable to adjust. I can estimate this model using OLS. That will give me consistent estimates under relatively weak conditions. I have a lag dependent variable, so I cannot expect the estimates to be unbiased. But under reasonable conditions, OLS will give me consistent estimates of these parameters. Based on these estimates, I can back out and get the estimates of the original partial adjustment process. For example, if I want to estimate the speed of adjustment parameter, I can see that since 1 minus lambda is equal to rho, lambda must be equal to 1 minus rho. And if I estimate my rho to be, let's say, 0.8, then my estimated speed of adjustment is 0.2. So just to summarize these results, if I combine these two equations, I get the ADL 1,0 model, where I have defined beta 1, beta 2, and rho as functions of the original parameters of the model, and I've defined a new sequence of error terms epsilon t. And that means that the partial adjustment model is really an ADL 1,0 process, and under reasonable assumptions can be estimated using OLS. Now this is a simplified version of the model. I've only included one explanatory variable in the latent variable model, but it's pretty straightforward to have more than one explanatory variable. The final model that we need to estimate will still turn out to be an ADL 1,0.